And really, we started talking about really nomenclature, which again is the way we go about naming everything. Remember that there really is sort of two types of compounds when it comes to naming, and then really when it comes to bonding, which we'll talk about a little later on in this chapter. We have ionic compounds. And really, if it is ionic, pretty much it will be a metal and a non-metal involved. And because of those periodic trends we talked about, what happens again when each of these guys get together is we are going to get a transfer of electrons from the metal to the non-metal. That's going to create ions for us. And again, we're going to get a cation, which is our positively charged guy. And that comes from our metal. And from our non-metal, we will get an anion, which is negatively charged. Again, in an ionic compound, there's absolutely no sharing of electrons happening. It is that electrostatic attraction between the positively charged ion and the negatively charged ion that holds it together. The other type of sort of compound that we talk about in terms of naming, or we'll get to, is covalent or molecular sort of compounds. These are really when we got kind of two nonmetals happening. The difference here, when we get a couple of nonmetals together, they have very, very similar sort of periodic trends, which means they both really do want to hang on to their electrons. They don't really want to give them away or anything like that. So here we are going to get some type of sharing of electrons happening. So we get no transfer of electrons, we get no ions or anything like that formed. We just basically have people sharing electrons. As we'll talk about in this chapter, again, it could be equal or unequal sharing. Okay, so with our covalent guys, we have equal or unequal sharing happening. And we started really off in terms of naming about ionic compounds. And when we do have cations by themselves, these are our positively charged ions, we really just use the whole name of it. So Na plus would be the sodium ion. If we had Ca2 plus, it would be the calcium ion. So any type of cation that's positively charged, you pretty much just use the whole element name for it. And if it happens to be the formula for the ion by itself, the cation, it does need charges, as we see here. So if you're going to write the formula of the actual ion or cation in this case, you do need to include the charges, and that's why we do include a kind of ion at the end of the name. For our anions, those are, again, our negatively charged guys. We take the root of sort of the non-metal name, and we kind of drop the end or a little bit more than the end. And those guys get the IDE sort of ending to their names when they are negatively charged ions. So again here, O2 minus is going to be the oxide ion, again based off of oxygen. Cl minus would be the chloride ion stuff. So again, same idea. If you're asked to write the formula for the anion, which again should have a charge, you should include the charges. And again, if you need to name them, IDE at the end. Remember that when we do put an ionic compound sort of together, when we take the ions, basically the cation and the anion, and put them together, we always want to make sure that the overall charge, when we take all the positive guys and all the negative guys and slap them together, we want the overall charge basically to be 0. And we want to get it to 0 in really the simplest way possible to get to 0. So when we do take a cation and put it together with the anion, and by the way, that is the order as well for both the name and the formula. It should always be the positive guy first, followed by the negative guy. We want really for the formula of these guys, no charge overall. So that's why when we take something, say like calcium, and we take something like chloride, when we put those two ions together, we pretty much want to equal 0. So really the simplest way to figure out the number you need, if you can't sort of visually see it, is you could just essentially multiply the charge numbers together. In this case, 2 times 1 is 2. So they both pretty much need equal 2 to equal 0, basically, when we put them together. Calcium is good to go with 2. here we have -1, which means we need one more of those Cl minuses. That gives us a grand total of -2 to balance out the +2. And at this point, you frankly could just write what you wrote there. We have 1 calcium and 1 and 2 of these Cls. And that would be the proper formula for what's known as calcium chloride in this particular case. And again, the overall ionic compounds formula should never have a charge. So it always wants to equal 0 in the simplest way possible. But you do need to remember that it is really made up of two things that does have charges. So this thing is really made up of this calcium ion that has a +2 charge, and it's made up of 2 of these Cl minuses. And again, it's not made up of Cl2 minus or anything like that. Again, it's made up of these ions, which is Cl minus each. We know that because we also talked about the periodic table. And again, there are certain things on the periodic table, right, that have fixed sort of charges. Everybody in group 1 is +1. Everybody in group 2 is +2. Really, in group 3, aluminum is mainly who you're talking about. We do skip 4 as we kind of have the staircase coming through there. 5, 6, 7, and 8. For our nonmetals, -3, -2, and -1 for group 5, 6, and 7. In the transition metals, which are over here, we have zinc and cadmium and silver. They have fixed charges of +2 for both of those guys and +1 there for silver. So again, there are certain things that have sort of fixed charges, and that's how you can sort of figure out, what the charge is on everything. Thank you. From those guys. Everybody else in the transition metal region, as we talked about last time, as we'll talk more about today, and a little bit outside of it, does have a variety of charges or variable type charges. So it does sort of depend on who it's attached to as to what the charge may be. Now, with that being said here, we talked about type 1 ionic compounds. And in type 1 ionic compounds basically are metal and non-metal. And as I mentioned last time, pretty much when you're doing naming, if you have a metal involved, it is really the most important thing in terms of how everything is named. So it's really the one that you should focus in on. And what makes it a type 1 metal, it's sometimes referred to, is these are the guys with the fixed positive charge. So these are any metal that comes from group 1, 2, 3, silver, zinc, or cadmium. And if you have basically an ionic compound that has one of those type of metals with a non-metal, the way we go about naming these guys is pretty straightforward. We just use the whole name of the metal. And again, our non-metal name will get that IDE treatment at the end. So remember that last time, as we also talked about, it does not matter how many of each of these things you have, how many metals you have, how many non-metals you have in the formula. It has no effect on the actual name. Again, we do not use any type of prefixes with a metal. So again, if you're finding yourself using a prefix with the metal, probably 99.99% of the time, you are doing something incorrect. Yeah, so you should never really use any type of prefix with that. And again, it's a very common mistake people make because they're like, seem like I should throw down some type of prefix, make it look fancier or something. Any questions on any of that stuff we talked about? I think we did an example there at the end, both writing the formula and also giving the names. Yeah. Any questions? All right, then let's continue on to the next part of it, which is type 2 binary compounds. So here's the deal with type 2. Type 2 is still ionic, which means you still have a metal and a non-metal. And again, as I just mentioned, that is the most important guy there, our metal. The difference with this type of metal versus type 1 is it is going to be probably a transition metal or just to the right on the periodic table. Things like lead, tin, etc., and that sort of area on the periodic table. What all these metals have in common is they can have a variable positive charge. Which means, frankly, the good news is it's really still named the same way as type 1, which means you're still going to use the whole name of the metal. You're still going to take the non-metal and drop the IDE at the end of it, obviously, and take out some of it. The additional thing that you have to do is in between the two, you need to put a Roman numeral. And the Roman numeral indicates the positive charge on a metal. So this is also something that people, frankly, screw up on because they think a lot of times that the Roman numeral is how many metals you have. It is not how many metals you have. It is if you took one of those metal ions that has a charge and you took it out by itself, it is what is the positive charge on it? What is the number for the positive charge on it? That is what the Roman numeral indicates. So for example, if we look at our guy here, which is FeCl2, first off, you still want to sort of identify what you're dealing with. So Fe is iron, which is a metal. Check. Cl is a nonmetal. Check. So right off the bat, we do know that it is an ionic compound because we have a metal and a nonmetal together. Once again, once that metal's in play, that is definitely where we should focus in on. And when we look at the periodic table for iron, should be dead there in the transition metal region, right around 26. And that also then should tell us, oh, it's a type 2. It can have a variety of charges. So how do we know what the charge is on the iron in this particular case? The good news is in this type of situation, you will 100% of the time always know what the charge is on whatever it's attached to. So you can just kind of work your way backwards to figure out what the charge is. So frankly, here we know we have an iron. We're not 100% perhaps sure what the charge is on it. But we do know we have Cl there, and we do know that Cl is group 7, which means the charge on Cl should be -1, right? Because it's group number 7. We don't just have one Cl there, right? We actually have 2, which means we actually have one more of those guys, which means if we put this together, that's a grand total of -2 sort of happening for our Cls. And we know an ionic compound has to equal 0, and since we only have one iron, that means in this case, the iron is carrying a +2 charge. So that's how you can simply sort of figure out what the charge is on the metal. First off, any questions on that? Once you do that, you can roll right into the name. This is going to be iron. This is going to be Roman numeral 2. And again, the 2 is because of the charge, not how many metals you have. And the last part here is going to be chloride. Once again, no prefix because I got a metal involved. So no prefix. Doesn't matter. I have 2 Cl minuses. You still just call it chloride in this case. Question on that. So why do we need the Roman numeral? Well, we need the Roman numeral because the case of iron, you could maybe have FeCl3, right? And if we do this guy, we again have iron, which is a metal. We have Cl, which is a nonmetal, tells us it's ionic. We have iron, which is again our transition metal, tells us it's going to have a variable charge. So we can do the same thing. This case, though, we have not 1, not 2, but in this case, we actually have 3 of the Cl minuses, which means we got a -3 happening. That means to balance it out, the iron in this case is actually going to be +3 to balance it out to 0. Remember, we need to kind of balance it out to 0. And that means that the name of this guy would actually be iron Roman numeral 3. And again, would still be chloride. And once again, the 3 is for the charge on the iron. So because these metals can have different types of charges depending on who they hook up with, you basically got to tell the person like, hey, in this case, we're talking about the iron with the +2 charge. In this case, we're talking about the iron with the +3 charge. Any questions on that there? So again, type 2, still ionic, still metal, non-metal. The base of the way you name is pretty much the same, but you got to take that additional step to figure out the charge on the metal and then insert the Roman numeral for whatever the charge is. Again, if you just took one of those metals out by themselves, what the positive charge would be, the number basically in that case. Any questions on that there? All right. So let's take a look at, say, this one here. Okay, so let's take a look at this one. Once again, we want to identify what we're dealing with. So Pb is lead, which is a metal. Oxygen is O, which is a non-metal. So we definitely have an ionic compound. We want to look at the metal, which is lead. It is technically, if you look on the periodic table, not a transition metal, but it is to the right and below the staircase, right about there. And again, those they're not transition metals, but kind of metals underneath the staircase to the right are basically named the same way. It basically means it does have the ability to make different types of charges. So this is going to tell us it's a type 2 situation happening. So again, we do the same thing. We got one lead. We have oxygen, which is group number 6 on the periodic table. I remember that. That is going to be a -2 charge. And there happens to be not one, but two of those. That is a grand total of -4, which means in this case, the lead actually is a +4 situation. So this should be lead Roman numeral 4 because of the charge. And again, this would be oxide. Now, I might have mentioned this last time, but let me re-mention it, that sometimes people are just taught to blindly do this move, where they just kind of move the numbers up and down. And again, it works about 94% of the time. This would be a case where it does not work. So again, maybe it's better just to do it the other way so you can visually see it, because I can't tell you how many people, maybe some of you have it on your paper, might have lead 2 oxide by just kind of randomly moving those numbers over there, which would be incorrect in this case. So again, just blindly kind of moving the subscripts up or the charges down works about 94% of the time. So if you're good with that, you can roll with that blindly, but sometimes you may just want to kind of think about what's going on there. Any questions on that there? Okay. Now, there is an older sort of system of naming these guys without Roman numerals. We personally are not going to roll with that, but sometimes you still see some names used. So the one that has the larger positive charge will end in ic, and the one with the lower positive charge on the metal will end in ous. And they kind of use the old kind of school name, like instead of iron, they'll go ferric or ferrous. Instead of copper, they'll go cupric or cuprous. I would say those two are very commonly still used, but we will not use it for here. We will strictly use Roman numerals along the way. Speaking of Roman numeral, here are some other sort of obviously type 2 sort of charges, multiple type charges. I will say the one that also confuses people is mercury. And this is mercury here. And this is mercury here. Oddly, the mercury that has all the 2s is actually mercury 1. And the one that has just 1 2 is actually mercury 2. And that's because mercury 1 actually comes as a dimer. It's actually 2 mercury 1s together. So when they get stuck together, that is why there's a 2 on the bottom, because there's 2 like atoms of it, and each one's +1, which gives you a grand total of +2. How do you know if you're dealing with like the mercury 1 or the mercury 2? That 2 on the bottom tends to stick around. So if you had something like this, for example, versus something like this, yeah, oxygen in this case is -2 in both cases. So you can see the extra 2 is here on the bottom, and that would be mercury 1 oxide, the guy on top. This one does not have the extra 2 on the bottom, and that would be mercury 2. So for mercury 1, that extra 2 on the bottoms tends to still kind of hang around in the formulas, and that's sort of how you know it is. They both obviously have a +2 charge, but again, that mercury 1 has a little extra 2 that sticks around on the bottom. Question on that there. All right, so as we talked about here, again, we're going to use Roman numerals to indicate the charge on the metal. We're still going to always go positive and negative, always 100% of the time. You got positive and negative ions coming together, positive first, negative second, both in the name and the formula. All right, so why don't you try a couple of these, and I'll give you a few more here. Let's do some formulas for, let's do something. I don't know, let's do chromium. For oxide, let's do tin to phosphide. And let's do copper to bromide. All right, so let's do some. Okay, let's take a look, see how you're doing. So we'll start over here on the left. We have CO, which is cobalt, that's a metal, and Cl, which is chlorine, which is a non-metal. So that automatically tells us we're in the ionic sort of situation happening because we have a metal and a non-metal. We're going to look at the cobalt, which is our metal, which is the most important thing there. And we will find cobalt there in the middle-ish of the transition metal region, right next to iron. And that should tell us it is a type 2 situation happening. So that does mean we need to take that additional step and figure out the charge on it. So once again here, we do have one cobalt. We do know that Cl is group 7, which should be -1, and there are 3 of them, which gives you a -3. So again, in this case, a +3 for our cobalt to balance it out to 0. That means we're going to go whole name here, cobalt, again, Roman numeral 3 for the charge on it. And again, it doesn't matter. We have 3 of the Cl's there, just going to be chloride at the end. Question on that name there. All right, next is our friend Cu, which is copper. That's a metal. I is iodine, which is a non-metal. So once again, that is a metal non-metal combination, tells us it's ionic. Once again, once that metal's involved, that is where we want to look, and we will find our copper there next to zinc in the transition metal region, which tells us it is type 2. So once again, here we need to figure out our charge. Our I, which is group 7, we know it's -1 in this case. So simply to balance it out, we would need a +1 there for our copper. And then we would go copper, Roman numeral 1, iodide, IDE at the end of it, again, because of the charge. This would be the formula for the anion. If you needed to write the formula for the anion, it has a charge. This would be the formula without the circle there, would be the formula for the cation. This obviously would be our cation formula. And one of these guys here would be our anion formula. Any questions on that one there? Coming to the last one, Sn is actually tin, which is a metal, and Br is bromine, which is a non-metal. So again, ionic. Tin is not exactly a transition metal, but it is one of those guys to the right of it underneath the staircase if you look on the periodic table. So it does have a variable charge. So same idea, our tin, we're not sure. I do know that guy is group 7, which means it should carry a -1 charge. And once again, there are 4 of them, which if we sort of add all those guys together, that's going to give us a -4, which means our tin in this case will have a +4. And that will give us a name of tin Roman numeral 4, once again for the charge, and bromide. Any question on any of those names there? All right, going the other way there, we want to write our formula. We see chromium, which is a metal. We see oxide, which is oxygen, is a non-metal. So we know it's ionic. So we know we should have things with charges. Good news is here, chromium Roman numeral 4 tells me the chromium has a +4 charge, right? So we don't have to figure anything out. Actually tells me it's a +4 charge. Oxide is oxygen, which is group number 6 on the periodic table, which tells me it has a -2 charge. Again, in this situation, really 4 is what we need to get to 0, and we do need not one of these guys, but we will need 2 of those guys to get to a -4. And that means all we have to do now is count how many we got. We got 1 of those and 2 of those, and that will give us our proper formula here. Yeah. Any questions on that? By the way, another one, if you just kind of move those things down, you will have the wrong formula. Yeah, so again, just don't blindly move things down and up. Here, same idea. Tin Roman numeral 2 tells us that's a metal, and phosphide is phosphorus, which is a non-metal on the periodic table. So tin with the Roman numeral 2 means it has a +2 charge. Phosphide is group 5 on the periodic table, which means that is 5. I was gonna write 5 there. It has a -3 charge. And in this case, if we just think about common number there, 3 and 2 is 6, basically. If you just multiply them together, you get 6. In this case, we got to get to 6 to get to 0. So to get the 10 to 6, we need not 2, but we actually need 3 of those. That gives us a +6. To get the phosphorus to 6, we need 2 of them. That gives us a -6. That means that the formula here, I'll go above, we have 3 of these guys and we have 2 of those guys. Yeah. Any questions on that? And again, if this helps you to do like I'm doing, kind of drawing out everything, do it. Because at the end, all you have to do is just count, right? 1, 2, 3 of those, and 1, 2 of those, right? And then you have their formula that you need without having to maybe think about it. Lastly here, we got copper Roman numeral 2. So that tells us transition metal, copper +2. Bromide is bromine, which is group 7, and that is a -1. In this case, we actually will need more of the Br to get to 2. And that will give us a -2 and a +2. So again, here we have 1 copper and 2 of these guys, right? Any questions on any of those there? Yeah. So again, these are all ionic compounds. And as you can see, hopefully metal is the most important thing. And still no prefix here with any type of metal or anything like that. So don't use it. Any questions on that there? Now, before we get to the next topic here, just a summary here, what we've been talking about. Again, ones that do not need a Roman numeral metals, anybody from group 1, 2, 3, silver, zinc, or cadmium. And again, pretty much everybody outside of that in the transition metal region will need it. Now, before we go on, I'm going to talk about hydrogen, H+ specifically. And hydrogen, although it is a non-metal, for the most part, in terms of how we name it, a lot of times is we name it very much like a type 1 ion. So even though technically speaking, it's a non-metal and will share electrons, there are certain properties of hydrogen that, especially when it's in the solution form, makes it very similar and will make an ion, and it'll be like a type 1 ion. So with that being said, if you did have something like HCl, that's a gas, for example, we would just use hydrogen, whole name, and chloride, last part of it. It doesn't matter if you have more than 1 hydrogen, in this case, H2S gas, which you never want to smell. That is still going to be hydrogen, and this would be sulfide. The reason we have a 2 there is because sulfide is -2. So we will need 2 of those guys to balance it out. And over here, this is Cl- and H+. So hydrogen is kind of an unusual thing, even though really in both of those cases, there's actually sharing electrons, it's covalently bonded. In terms of how it's named, Typically speaking, we just kind of do it almost like a type 1 metal, even though, again, it's a non-metal, and we just use the whole name of hydrogen regardless of how many you have. And the second guy gets basically the non-metal with the IDE treatment. Any questions on that there? Now, if these guys end up being acids, they actually are named slightly different as well, but you know, that's how we would name these guys. They're gases. All right. Now, there's a decision tree, again, type 1 versus type 2, in case you need to. Again, type 2, only one with a Roman numeral. Now we're going to talk about type 3 binary compounds, and these are covalent guys. These are covalent, molecular. These are basically two nonmetals together. Here we're going to have sharing of electrons. And after all the talk of don't use a prefix, don't use a prefix, this is the appropriate place to actually use a prefix. So in this type of naming, we actually roll with prefixes here, and this is the correct place to sort of use prefixes when you have it. So to name type 3 binary compounds which contain only nonmetals, they are probably the easiest ones to do, but also probably the ones most people screw up on because they go, it can't be that easy. I should do some other stuff you shouldn't do. And they end up with the wrong name. So again, here, we basically don't have to worry about charges. There's no ions here because they're sharing electrons. So really all you have to do in this situation is basically we use the whole name of the first element, and the second element gets the nonmetal sort of name with the IDE. The additional thing that we use is we use a prefix if necessary, and a prefix which is usually necessary. So we sort of add prefixes. So these prefixes, as we'll see a table here, we have mono, which is 1. We have di, which is 2. We have tri, which is 3. We have tetra, which is 4. We have penta, which is 5. We have hexa, which is 6. We have hepta, which is 7. We have octa, which is 8. A little nona, perhaps 9. A little deca is 10. So we use these prefixes, but there are some sort of type 3 guys that we really just roll with common names, and we might have saw some of them earlier. A reminder that, again, if you see H2O, that is just water. No type 3 naming, just call it water. If you have NH3, that is ammonia, also no type 3 naming. And if you have CH4, that is methane. So these guys go by common names, even though they are non-metal. Non-metal, so always use sort of those names here. So there are a few rules for these prefixes that we do want to follow, and the major rule is we do not use mono on the first name, but it's okay on the second. So we do not use mono on the first name. But again, it is okay on the second. The other sort of major thing that occurs when we use these prefixes is sometimes we get a couple of vowels that back up to each other, like a couple of O's, an A and an O that sort of backs up. So for example, if we look at CO as capital C, capital O, that is carbon, which is a nonmetal. That is oxygen, which is a nonmetal. As soon as you see that, that tells you it is type 3 time. You don't have to worry about charges, balancing anything. You frankly just need to pick the proper prefix. We have basically one carbon. We do not use mono on the first name, so we just roll with the whole name here of the first element, which would be carbon. Here we have also one oxygen, and the prefix for one is mono. And the nonmetal does get the IDE treatment here. And this is a situation where we do get, as you see here, and this is what I'm talking about, a couple of O's that are backed up to each other here. We do not call this carbon monoxide, right? We call it carbon monoxide. And typically speaking, when you get a couple of O's that back up from the prefix ending to the element first letter, we drop the vowel in the prefix, basically, and this would then become monoxide. Again, 1O. Other common sort of places where we have that, you got a couple of O's, drop that O. An A and an O is also usually a situation where we drop the A off of the prefix and kind of just leave the O. Oddly speaking, a couple of I's are usually okay. So if you got a couple of I's that kind of back up to each other, that's okay. But those are the two main ones. No two O's in a row and an A and an O. Again, drop the vowel off of the prefix. Question on that there. So rules for naming this, again, the first element is always in the formula named first. The second one, again, pretty much gets that IDE treatment. We use the appropriate prefix, again, on first and second name. The only prefix we do not use on the first name is mono. And here again, it's a table, those prefixes, and as I mentioned, you know, where we drop the A and the O and the O. Too bad. And here's a couple of other examples of that. Again, the AO here, we're going to drop the A off of the prefix, and we get the RO, and that is our O off of the prefix there as we transition. Again, here are just our common names for methane, CH4. Yeah. Once again, nobody wants a refreshing glass of dihydrogen monoxide, right? So we all want a glass of water. Make sure you do call it water, not a trick question. All right, let's try some here, maybe. So for each of these, give the name. I'll give you a couple more here to write some formulas. Let's do nitrogen, pentoxide. Let's do sulfur hexabromide. And let's do dioxygen and make something that doesn't exist. Dioxygen. Tetrachloride. Pretty sure that doesn't exist. All right, let's go. Names on the look. So let's take a look here. These really should probably be the fastest ones that you do because, frankly, there's nothing to balance. There's nothing. You just pretty much got to pick the right prefix and all that good stuff. First off, though, we nonmetal tells us it's type 3. That automatically tells us prefixes. So again, we just need to pick the right prefix. So I has 2 of them. So 2 prefixes di. And again, here on the first element, we're just going to go with the entire name. So this would be diiodine. The second guy, that is 7, prefix is hepta. And oxygen gets the IDE treatment for the second name. And here we are going to drop the A off of the prefix so we don't get that A and O backing up to each other in this case. So a little diiodine heptoxide in this case. Question on that one there. You don't. The 2 I's are okay, oddly. So it's mainly double O's or an A and an O is really the ones to just worry about. Other questions? Here again, we see carbon nonmetal, oxygen nonmetal tells us type 3. Roll right into it, pick the prefixes. Here we have 1 carbon, and that is mono. Do I use mono on the first name? I do not, so we just get rid of the mono, and we just use the whole name of the first element, which is carbon. Here, di is for our 2 there, and again, oxide, the IDE ending there for our oxygen. Lastly, here we have phosphorus, which is a nonmetal, chlorine, which is a nonmetal. So that tells us it is prefixes in type 3 situation. Once again, here we have just one of the P's, and that means that's mono, which we're not going to use. So that is phosphorus. And here we have 3, which is going to be tri, and then IDE, yep, trichloride there. Any questions on any of the names there? Now, what I think should be like your super fastest move is the guys on the right here, because frankly, as soon as I read the name, I see di and penta, basically. Those are prefixes, which tells me I don't have to worry about anything but write what it says. So di is 2, nitrogen is N. That's an N2. Penta is 5, oxygen's O, O5, right? So those you can really just jam right through as long as it's a type 3. Here, same idea, sulfur, no prefix, but I do see hexa, which is a prefix, and I know pretty much prefixes are only going to be there in type 3. So sulfur with no prefix means mono, so that's just an S. And hexa is 6, and Br is bromine. And there it is, yeah. Again, we don't have to balance anything because there's no ions in this case. Everybody's sharing electrons. And now my made-up thing here, dioxygen tetra. So we see a couple of prefixes. Once again, O is oxygen, di is 2, Cl and 4. Yeah, there it is. Any questions on any of those there? So this is the proper place to use prefix and really kind of the only place with a little hashtag there. We'll figure it out there in a second. But this is pretty much the only place really to use prefixes in this situation. Any questions on it? And again, you don't have to balance anything, just the right prefix, put them together correctly. Okay, we're going to continue on here. Any questions on type 3 compounds here? So again, as bad as it may sound, don't overthink these. Yeah, so just roll with it, the prefix and all that good stuff. So again, just to review the different types of compounds we've been talking about. Again, type 1 ionic compound, metal, non-metal, metal important, fixed positive charge, whole name of metal, IDE ending for the non-metal. Type 2, also metal, non-metal, and ionic. Metal important one there has a variable charge, which means you do need to figure out the charge on the metal. Use a Roman numeral to indicate the charge. Whole name of the metal, Roman numeral, and IDE for the non-metal. And as we just saw there with our type 3, these are two non-metals together, covalently bonded. Again, here we're going to roll with prefixes. Again, with the few little things, no mono on the first one, okay on the second, and those couple vowels that back up to each other. Now, the sort of last type of naming we're going to talk about is ones that contain polyatomic ions. And for example, a polyatomic ion are actually groups of nonmetals that are actually sharing electrons and covalently bonded together, but they actually still have charges, which makes them ions. They're kind of weird things that are really covalently bonded, sharing electrons, but still, because of how the electrons are shared, they actually end up with an overall charge. So, for example, here, if we look at this guy, NH4NO3, if we break it up right about there between those two, we actually have two polyatomic ions. This guy right here is actually NH4 plus. That one nitrogen and 4 hydrogens, they all stay together and move around as whole units. They never break apart into individual things. They just move around as a group, and it has a +1 charge. We will learn how to draw it later, but just to preview, it actually looks like this is basically what we have there. So this whole thing is sharing electrons and moving around, and the overall thing has a +1 charge. This guy is also a polyatomic ion, and this is the 1 nitrogen and 3 oxygens. Once again, also moves around as a unit. They do not break apart into individual elements or anything like that, and it has a -1 charge. We will also learn to draw this guy later on, and it looks something like this, by the way. So ultimately, when we put this together, we actually have two things with charges. We have a cation, which is our positive charge, and we have an anion, which is our negative charge. That is why when we put it together, like we've been doing with things with charges, it needs to equal 0, right? So this guy is +1. These guys together, we just need one of each of them, which we actually get to that formula of NH4NO3. Once again, you can think of this much like our ionic compound, which is the overall compound when it comes together has no charge, but it is actually made up of things that do have charges. So it's very similar to type 1 and type 2 sort of compounds. Now, each of these polyatomic ions has a special name. This guy here is known as the ammonium ion, not to be confused with NH3 that does not have a charge and is known as ammonia. So ammonia, no charge, 3 hydrogens. Ammonium, 4 hydrogens plus 1 charge. So again, those two things are very commonly confused. This guy over here, by the way, is known as the nitrate ion. The good news about polyatomic ions, there's not much, but the good news is pretty much just use their names, regardless of how many you have. So when we have something like this, the name of this guy is ammonium. Name of this guy is nitrate, and you just put them together, and that is ammonium nitrate. So each of these polyatomic ions, we'll see a list here in just a second, they actually have specific names. And when you use their names in naming, it doesn't matter how many you have of them, you just simply just use the name, whatever the name may be. Now, with these polyatomic ions, I will say that probably, for the most part, this guy right here is one of the few positive polyatomic ions that you'll come across. So there are a couple of other ones, but ammonium is probably the very few positively charged polyatomic ions. Most of them will be negatively charged. And since there's not that many positively charged polyatomic ions, what typically happens with polyatomic ions are they will hook up with metals. And you typically will get metals and a polyatomic ion. Now, as we talked about previously, right, whenever a metal is there, it is still the most important thing. The metal is going to determine whether or not it is a type 1 metal, which does not need a Roman numeral, or it's a type 2 metal that would need a Roman numeral. For example, if I take this NaNO3 and I break this right about there, that is our friend sodium, which is group 1, has a +1 charge, right? That is our friend nitrate that we just talked about, has a -1 charge. That again is why we only need one of each of those when we put it together in the formula. +1 -1 equals 0. This guy is the most important thing. Do I need a Roman numeral when I name it? I do not. It is a fixed positive charge, which means this would be known as sodium, and the whole name of this guy is nitrate. So that would be sodium nitrate. So the other thing is we could have this guy, for example. That is Fe, right? Which is iron. That is nitrate, which is a non-metal. Do I need a Roman numeral for my iron? I do, because it's type 2 and it is in the transition metal region. That is a type 2. We do the same thing. Fe, I'm not sure, but I do know once I learned my polyatomic ions that nitrate is -1. By the way, there's not just one of them, but there are 2 of them, which means the nitrate is contributing how much of a negative charge in this case? -2, right? Which means my iron should be +2, just like we did previously, right? So this would be iron Roman numeral 2, just like before. And even though we have 2 of these guys, we just use the whole name of the polyatomic ion, which is nitrate. First off, any questions on that there? By the way, what else did I write in my formula when I had more than one of those polyatomic ions? I put in parentheses. Because if I did not put in parentheses and I wrote it like this, FeNO32, what does that mean? Means I have 32 oxygens, which I really don't have 32 oxygens and only one nitrogen. What I'm trying to say is I have two of these units, right? So whenever you have more than one polyatomic ion in a formula, you need to lay up some parentheses around the polyatomic ion and put the number to the bottom right of how many of those units you have. Now, if you just have one, you do not need the parentheses, but definitely if you have more than one, you do need the parentheses. Otherwise, you'll be saying something you really don't mean, like you have 32 oxygens, for example, which clearly you can see. 6, right? We also have one nitrogen, two nitrogen. One is 2. That's basically what we're saying when we put the parentheses on the outside. Question on that. So I would say probably 99 times out of 100, you're going to find your polyatomic ion hooked up with a metal. And what you really want to sort of fall back to type 1 or type 2 rules. Either you'll need a Roman numeral or you won't need a Roman numeral. And once again, the polyatomic ion will pretty much just be the name of the polyatomic ion, whatever it may be. Any questions on that there? So let's take a look at this list here. Here's a list of some polyatomic ions. So the bad news is, frankly, there is no other way other than you kind of have to learn them, right? So you got to learn them, the formulas and the names. But the semi-good news is there's a sort of easier way to learn them that might be easy for a lot of people. When you look at these polyatomic ions, there are numbers of ions that are related to each other. So for example, if we look at NO3 minus that we just looked at, that is nitrate. We look at NO2 minus, that is what is known as nitrite. If we look at SO4 2 minus, so the sulfur and the 4 oxygens all together with a -2 charge, that is what is known as sulfate. SO3 2 minus, 1 sulfur, 3 oxygens, that is known as sulfite. So when you have a grouping of polyatomic ions that is a grouping of 2, what we see is the only difference between, say, nitrate and nitrite is actually just the number of oxygens, right? They both have a -1 charge. They both have 1 nitrogen. One has 3 oxygens and one has 2 oxygens. The only difference between sulfate and sulfite is also the number of oxygens. They both have 1 sulfur. They both have a -2 charge. One has 4 oxygens. One has 3 oxygens. The one that has the most oxygens in a group of 2 will end in 8, typically. The one with the least number of oxygens in a group of 2 will end in ite. You think you ate too much, so the one with the more oxygens, right? Same thing here. More oxygens, 8. Less oxygens, ite. So a good way to remember these, for example, is you could either learn all the ites and know that if you need an 8, you just add an oxygen, everything else is the same. Or you can learn the 8s, and if you need an ite, you drop off an oxygen, everything else stays the same. So without having to learn each one individually, you could learn, and like I said, all the ones that are 8s are ites, and either adjust the oxygen up or down, depending on which one you learn. Now, there's also a group of 4 that are related to each other, and that's these guys right here. That is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. So ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. So if we break it apart right about there, they all have a -1 charge. They all have chlorine. Again, the only difference between all these guys is the number of oxygens, right? So we know from our conversation a second ago, the 2 on this side have the least number of oxygens, which means they should end in ite, right? So that would be chlorite. This guy here would be chlorite. But obviously we cannot have two names or the same name for two different things. So in a group of four, the one with the least number of oxygens, in addition to ending with ite, you put hypo in front of it. You put hypo in front of it. So that is known as, the guy next to it is chlorite. We also know that these two have the most oxygen, which means they both should end in ate. So that's going to be chlorate and chlorate for this guy as well. But again, we can't have the same name for two different things. So in a group of four, the one that has the most oxygens will actually start with per in front of it, chlorate. So that is perchlorate, chlorate, chlorite, and hypochlorite. So if we have a grouping of four that are related to each other, we have those additional things that go in the front of the names. Per for the most, hypo for the least. That's what hypo means, less. So that's a good way to remember it. Hypo means less. So it's the least number of oxygens. We'll start with hypo. By the way, it doesn't matter. Cl is group 7. So you could actually swap out the Cl for anybody in group 7. So instead of ClO3 minus, which is chlorate, if I had BrO3 minus, what do you think that would be called? That's not chlorine, but that's bromine. So that would be bromate. Yeah. So you could actually swap it out. Put an I in there. That's iodate. So you could swap it out for anybody. Put an F in there, fluorate. So you could put any of those halogens in there, and they're all sort of named the same. So that's a very common thing. I would say that's probably your most common group of four there, the ClO4 minus, the ClO3 minus, the ClO2 minus, and the ClO minus. There are a couple of other things that you'll see when you look at this list. You have something like CO3 2 minus. This is carbonate. Sometimes they will put a hydrogen, an H plus in front of it, which means you have HCO3 plus 1 minus 2 leaves you a minus 1 left over. I basically just put hydrogen in front of it. So creatively, this would be called hydrogen carbonate, because I put a hydrogen in front of carbonate, basically. To further be annoying, this is also known as bicarbonate, or some bicarbonate that you might need right about now for that heartburn. And that's something that's still used. So bicarbonate is used instead of hydrogen, so bi instead of hydrogen. Also bisulfate is also used, as you can see here. So bisulfate, bicarbonate is also very, very commonly still used a lot by people. There are also some polyatomic ions that end in ID. That is hydroxide, OH minus. CN minus is cyanide as well. So there are a few that do end in IDE along the way. So again, I would recommend you do need to know some of these here. So that again is a good way, kind of group them together and decide how you want to kind of remember them. You do need to know the name and the formulas with the charges, so you can write the formulas and all those things together. Here's another sort of table, similar table. So why don't we try some here? Why don't you give the name for these things? Let's go with not that. Let's go with this here. Let's do and why don't you write formula for ammonium sulfide? Let's do nickel for hydroxide. Actually, no, let's not do it. Let's do cyanide. And let's do LiHCO3. All right, so why don't you do names on the left and proper formulas there on the right and see what Okay, let's take a look. So once again here, I see a metal and I see a polyatomic ion. So again, always metal involved. That's the most important in terms of the naming. That is copper, which is a transition metal. So that means it could have a variable charge. So we're really going to take kind of a type 2 approach here because of the copper that's present. That means we probably want to figure out what the charge is on it. Once again, once you learn these, you'll see that is nitrate, which is NO2 minus. Again, there's parentheses and a 2 on the outside, which means we have not one of those ions, but we do have two of those ions. That's what, again, those parentheses mean. That means in terms of the negative charge, -1 is -2. That means that our copper in this case would have a +2 charge, again, to equal 0 like we did previously. And that's all we need to name it. Again, we're going to go with copper. We do need a Roman numeral of 2 for the charge on the copper. And again, even though there are multiples of this polyatomic ion, we just simply use the name of the polyatomic ion, which in this case is only 2 oxygens. So that is nitrite. So that would be copper, Roman numeral 2, nitrite. Yes. Because nitrate is NO3, right? So again, it has more oxygens. By the way, if I didn't know the NO3 was nitrate, knowing that that's nitrite, ITE, again, more oxygens would be just one more, and it would be 8, right? So just NO3 minus. Here we look at calcium, which is a metal. Again, OH is hydroxide, which is a polyatomic ion. Once again, it is the metal here that's going to determine our naming. And in this case, we do not need a Roman numeral, right? Because that is a type 1 metal, a group 2, which means in this case, we don't really have to figure out anything. We just need to roll with the whole name, and that would be calcium. And again, even though we have 2 of those hydroxides, we just use the whole name, and that would be hydroxide, which would be somewhere it was here, right there. The reason we do have 2 hydroxides is calcium here is +2, and each of the hydroxides are -1. So again, properly to balance out the formula, we need 2 of those guys to balance out the +2 charge that's on the calcium. Any questions on that one there? Coming here, we have iron, which is a type 2 metal, and sulfate, which is a polyatomic ion. Because that is a type 2 metal, we do need to figure out the charge. So we have an iron. We know that sulfate here is right there, SO4 2 minus. That means to balance it out, this would have to be a +2 in this case. And that would give me iron Roman numeral 2, again, because of the charge. And the whole name of that guy, which is sulfate, ATE at the end of that guy. Question on those names there. My late addition here is CR, which is chromium. That's a metal. PO4 is phosphate, which is a polyatomic ion. Chromium, again, stuck right there at 24 on the periodic table. And that is in the near the middle of the transition metal region, or for sure. So that means that it does have a variable charge, so we do need to figure it out. So in this case, we actually have not 1, not 2, but we actually have 3 chromiums happening there, right? That's basically what the 3 means. We got 3 of those. And in this case, we actually have phosphate, which is PO4 3 minus, and there are 2 of them. That means the phosphate here is contributing a grand total of -6. That means each of the 3 chromiums would have what type of charge to get to 6? Yeah, 6 divided by 3 is 2, +2 for each of those, right? +2, +2, +2 is +6. That means that's going to help us with our name. This should be chromium, Roman numeral 2, not 3. 2 because of the charge if we took one of those guys down. And again, even though we have multiples of those guys, it is going to be, go this way, phosphate. ATE. Yeah. Any questions on that one there? Question on the names. Yeah. All right, so let's write the formulas here. So we have ammonium. That is a polyatomic ion, which is, as we saw earlier, NH4 plus, right? Sulfide is still sulfur off the periodic, just sulfur off the periodic table. Group 6, which is a -2. In this case, to balance it out to 0, we actually need more of that guy, right? We need a grand total of 2 of them. So we need one more of those guys. That is a polyatomic ion that I have more than one of. That means I also need to put a parentheses around it and a 2 on the bottom. And I just need one of the S's there. So again, you need to make sure that you put parentheses around the polyatomic ion if you have more than one of them, which in this case, obviously, we have 2. Any questions on that one there? Nickel Roman numeral 4 means my nickel has what type of charge? +4. That's pretty much what the Roman numeral means, right? Cyanide. I saw this on here before I was scribbling all over the thing, which is right about there, I think. And that is actually Cn minus, right? So in this case, we actually need more of the cyanide, right? We need a grand total of 4 of them, right? That will give us a -4 to balance out the +4 charge. So that means my formula here would be Ni. Once again, multiple polyatomic ions. Parentheses, number on the bottom, right? Of how many we got going on. Question on that one. And again, you can do the same thing as we did before, just count them. 1, 2, 3, 4. Just got to make sure parentheses, a polyatomic ion. Lastly, here we have Li, which is lithium. HCO3 is HCO3 minus. That is our bicarbonate, our hydrogen carbonate that we were talking about previously, right about there. And that means, though, we are going to still look at the metal, which is lithium. That is a group 1 metal, which means it's a type 1 metal, has a fixed charge. Means that's all I need. I'm going to go whole name of that metal, lithium, and also whole name here of my polyatomic ion. This one you could either write out hydrogen carbonate, or again, you can, if you wanted to, go lithium and use bicarbonate as well. So that is fine, either one in that. Question on any of those. So as you can probably see here, in most of the cases, as I mentioned, you're probably going to have a metal, most likely hooked up with a or no Roman numeral. And again, you just got to get the name. That's for the polyatomic ion. Doesn't matter how many of the polyatomic ion is used, regardless of how many you have. Yeah. Any questions on polyatomic ions or naming? Yes. All right. Here. Talk about naming, and we talked about these patterns. Again, in a group of 4, we do add those kind of hypo and per along the way for the most and the less or least. And as I mentioned before, you can't swap that out for halogen. And we do add hydrogen or H plus sometimes before, because it's our hydrogen carbonate. So now we're going to talk about bond and demonstrate sort of what's going on with bonding. So as we talked about earlier, and I think we saw it, we can use Lewis dot symbols to help us understand bonding. Again, sometimes people just generically call these electron dot symbols, same idea. Again, a Lewis dot symbol or an electron dot symbol is pretty much the symbol, and one dot to represent each of the valence electrons that are present. Again, there is really no rule, as I might have mentioned before, other than we really don't go more than 2 per side. And obviously, that is 8 if you count all that up there. Most people kind of go clockwise one at a time, and then it really doesn't matter as long as you don't go more than 2. By the way, we could get the number of valence electrons, right? It's equal to the group number, right? So that is the quick way, right, to get our valence electrons. Everybody in group 1 is 1, 2, 3, 4, 5, 6, 7, and 8. By the way, 8's an important number of bonding. Who's number 8 on the periodic table? What group? Those are the noble gases. That is really the whole purpose of bonding, all bonding. Like the noble gases in terms of their electron configuration. So they want to be isoelectronic with noble gases. Noble gases are extremely stable, which is why they're chemically inert. And that's what everybody's really trying to achieve, both through ionic bonding and covalent bonding. Some cases it requires sharing of electrons. Some cases it requires electrons being transferred for that to occur. So there we go. By the way, one exception to group 8 in terms of valence electrons is helium. Helium only has 2 valence electrons because helium only has 2 electrons, so it can't have more. When it's part of group 8, it only needs 2. That's also why another really super important thing about bonding is, what is the noble gas that comes right after hydrogen? It is helium, which means hydrogen only needs to get to helium. And that means hydrogen should only have 2 electrons, as we will talk about many times. So if you're drawing hydrogen, it should pretty much just look like that. If you're drawing hydrogen like this, and dots and lines and dots, just make one of those because it's wrong. So hydrogen should only have 2. Beat that into your head. It's a super common thing. I've seen hydrogen, I don't know how many. Sometimes it has electrons, 42 sometimes. People just keep drawing lines and dots all over the place. So hydrogen only needs to get to helium. It only needs 2 electrons. Everybody else needs 8 to sort of be happy. But definitely hydrogen should only have 2, which is a really important thing to remind yourself a lot of. Now, we could use these Lewis dot symbols to help us identify what's going on. And the 2 types of bonding that we sort of talked about there with naming. Once again, ionic compounds, we're going to have our metals and nonmetals, and that's going to be a transfer electrons. So the idea here is, with those periodic trends, as we talked about, metals have all the trends that want them to basically give away their electrons. So it's like super easy in most cases for metals just to lay up and give away their electrons. And that works really well when they hook up with a nonmetal, because nonmetals have all the trends that make them want to gain electrons and keep their electrons and bring electrons towards them. And that is why when we get a metal and a nonmetal together, we actually get that transfer of electrons, because the metals are like, take my electrons, please. And the nonmetals are, I'll be more than happy to take your electrons. And we get those electrons completely being transferred from the metal to the nonmetal. That's what creates those ions we talked about when naming. That's what creates the cation that's positively charged when it loses electrons, and the anion where it gains electrons become negatively charged. That is different than what happens with a covalent compound and nonmetals, because if you look on the periodic table, all the nonmetals are upper right of the periodic table for the most part. They all have the same sort of periodic trends, which means they all pretty much want to hang on to their electrons. They're not looking to give away their electrons. They actually want to hang on to their electrons and actually bring electrons, more electrons, to themselves. So what happens when 2 nonmetals get together, neither one of them is going to lay up their electrons to the other one. So the best that they could do is go, well, I'm not going to give you my electron. You're not going to give me your electrons. Why don't we just share them instead? So we'll just settle on sharing the electrons. So that is why we do get sharing in the cases with 2 nonmetals, while we get that transfer of electrons when we get metals and nonmetals together, because of those sort of periodic trends. Any questions on that there? All right. So general rule, as we've talked about, pretty much our metals in group 1 and 2 will form cations, and our nonmetals will really form anions there as we go to the upper right there of the periodic table. So let's take a look at an example of lithium fluoride. So for example, lithium is group number 1, which means lithium, our friend, has 1 valence electron, which is the outermost electrons. The valence electrons are the ones involved in bonding. A throwback to a chapter there, 1s2, 2s1. That right there would be the valence electron we see in the dot. The lower electrons, right, are our core electrons. This is our valence electrons, right, involved in bonding. It's going to react with fluorine, which is group 7, which means it has 7 valence electrons. 1s2, 2s2, 2p5. This would be the 7 valence electrons there in fluorine. Remember that the numbers in front are the energy levels, right? So we got 7 electrons on the second energy level and only 2 on the first, which is our core electrons. So when these two guys get together, lithium is like, go ahead and take it. And he's going to send that electron over. The result of that is lithium at that point will now lose an electron and become positively charged because it'll laid off its electron. The fluorine in this case will actually pick up the electron. And it could do that because it's got room for it right about there, right? P subshell could hold how many electrons? 6. And it only has, in this case right now, 5. So it's got room for that electron that's coming on over to land. That makes the fluorine have a negative charge. This is an ionic bond. There's absolutely no sharing of electrons here. That is also why in my picture there are charges drawn. And a lot of times people put brackets around them to indicate that these are ions. They are held together by electrostatic attraction. Positive and negative attraction holds that together. What happens in terms of electron configuration in this case? Lithium gives away its valence electron, which means it ends up on the right-hand side with 2 electrons. Electron configuration of 1s2. 2 electrons on the periodic table is our friend helium. Yeah, it becomes the same electron configuration as helium. The fluorine has room for that electron right there, and that will then give it 1s2, 2s2, 2p6. That is 10, are our friend neon. Both of those elements, lithium, by giving away its electron, backs up on the periodic table. If you look at it, backs up 1 to helium, which is a noble gas. Fluorine picks up the electron, goes forward on the periodic table to neon's configuration, and they become isoelectronic with helium and neon. That is the purpose of bonding, because they now have the same electron configuration as the noble gases, who are super stable, and that is really the purpose of bonding, is for that to occur. As we might have talked about when we're doing electron configuration, we talked about things with charges. Does the lithium with a +1 charge and the fluorine with a -1 charge, which is lithium fluoride, by the way, right? Are those guys now helium and neon? Did they become those elements? They did not, because the only way they could become those elements is the protons would have to change. No protons change here, just electrons. So they become the same as the electron configuration for those noble gases. They are still lithium and fluorine because they have the appropriate number of protons. Remember, protons is the one thing that if you change the element, right? So here's just electrons. Question on that there. So that is what is known as an ionic bond. Again, that attractive force between the positive ion and the negative ion is what holds that unit together. That is a super strong attractive force, one of the strongest forces you could have, positive, negative attraction. By the way, the strength of that attraction increases with the size of the charge. So something +3 and -3 will be held together tighter than something, again, +1 and -1. So kind of that strength of that attraction gets stronger with a greater charge. Now, if we look at something like calcium oxide, calcium is group 2, which means that's got 2 valence electrons. And that's a little electron configuration of 1s2, 2s2, 2p6. 3s2, 3p6, 4s2. By the way, right there, that is also our friend there, argon 4s2 happening, right? These are the two valence electrons that we have in calcium in this case, right? On the 4th energy level, the highest. Going to react with oxygen in this case, which is group 6, has 6 valence electrons, a little 1s2, 2s2, 2p4 in this case. So again, when calcium, which is a metal, gets together with our oxygen, which is a nonmetal, going to send over some electrons. By the way, if calcium just gives away 1 electron, will it be happy? No, because if you look on the periodic table, calcium just gives away 1 electron. It goes back 1 spot. It's to potassium, which doesn't have the same ring as a noble gas, right? So calcium wants to give away not 1, but both of its valence electrons. That's going to allow it to be happy. The oxygen has no problem because, again, in that P subshell could hold 6 and it's got only 4, so it's got plenty of room for those 2 electrons that are coming in. And when it does so, the calcium will then have a +2 charge. Our oxygen will pick up those electrons. And because it picked up 2 electrons, will become a -2 charge. And again, it is that positive charge and negative charge that holds that together. In terms of calcium, it will lose these 2 electrons, which leaves it 18 electrons, and it will end up in argon's configuration. The oxygen will gain the 2 electrons there and become 1s2, 2s2, 2p6, our neon's configuration. Once again, both of these elements are able to achieve noble gas configuration, that nice stable configuration, by transferring electrons. So it's losing and accepting electrons. Here again, as we probably talked about, our metal backs up to the noble gas that comes right before it on the periodic table, and our nonmetal goes forward to the noble gas that comes after it on the periodic table. Question on that there. Now, what happens when we throw together 2 things we just did, which is calcium and fluorine? So let's say we put together these guys here. So calcium, again, a little argon 4s2, the 2 valence electrons. This is going to be 1s2, 2s2, 2p5, 2p5. So here, calcium is going to want to give away its electron. Now, as we talked about previously, right? Calcium wants to give away how many electrons? 2. Can that fluorine take any more electrons? Cannot, because it only's got room in this case for 1. So that's problematic because that's going to prevent calcium from doing what it wants to do. That's also why we don't need 1 fluorine in this case, but we actually need 2. And that gives this guy a spot to drop its other electron into, because this one can also accept an electron. And what that ends up doing is gives us calcium with a +2 charge, being able to give away 1 electron to each of the fluorines. 1 fluorine will pick up only 1 electron, which means it will become negatively 1 charge. The other fluorine will pick up 1 electron, which means it will become negatively 1 charge. Now, calcium was able to get rid of both of its electrons, which means it is able to hit argon's configuration. Now, each of these fluorines was able to pick up 1 electron in each, which gave each of these fluorines 10, which means each of these guys were able to achieve neon's configuration. All 3 of those things are now super happy because they've all hit basically noble gas configuration. Here's where I tie it all together, right? Earlier we talked about when I take something with a +2 charge and a -1 charge, overall charge needs to be 0 when you put it together, right? This is the reason why. Not really for the naming part, but to make sure everybody hits noble gas configuration. That is why the proper formula here is CaF2, because you need two of these guys to take in both of those electrons. And that is why when we talk about ionic compounds and we say when we put them together, that the positive guy and negative guy has to equal 0 in the simplest way possible. That is because that allows both of those guys or all those metals and nonmetals to achieve noble gas configuration when they come together. That's the reason why when we put it together to equal 0, it gets everybody to that noble gas configuration. As you can see here, right? 1 calcium and 2 fluorines, right? So that gives us our proper formula here in the simplest way possible. So that's really why when we have something that's positive and negative, we put it together, that we do need it to equal 0. It's really for the bonding aspect of it. It allows everybody to achieve noble gas configuration. Question there. Question on ionic bonding. So this is ionic bonding. Here you can clearly see when you draw ionic bonding, you do need to have the charges on the right-hand side to indicate that they are ions. That is different than covalent bonding that we'll talk about and how you draw those guys, but here you do need that. So let's talk a little bit about a covalent bond and sort of what happens with a covalent bond. I feel like my lines are way off here, so I'll just redraw these. They're sort of ish close. So Gilbert Lewis, hence Lewis structures, basically suggested a role of bonding by atoms actually sharing electrons rather than being transferred. And this is what happens when we get two nonmetals together. So for example, if we get hydrogen, which has one valence electron, together with another hydrogen that has one valence electron, because they are both hydrogen, for example, in this case, and they're both nonmetals, they pretty much have the same identical electronegativity periodic trends. Neither one of them is going to give away their electron. So the best that they could do is go, instead of we transferring, why don't we just share these guys? So those electrons are going to come together, and you could show that by putting 2 dots here. And the 2 electrons in the middle count for the hydrogen on the left. The 2 electrons on the right-hand side, or in the middle, count for the hydrogen on the right-hand side. By sharing electrons here, it allows both of the hydrogens in this case to achieve 2 electrons, right? And that gets our friend hydrogen, as we talked about, to where it needs to be, similar to helium in terms of their configuration, and makes a stable bond. You could represent that bond also by drawing a single line between them. A single line is a single bond, and that is basically a pair of electrons. There's also a double bond, which are 2 lines when you draw it, and that represents 2 pairs of electron, or 4 total electrons. And you could also have a triple bond, which is 3 lines, which represents 6 total electrons, or 3 pairs of electrons. So what happens is, right, there is a nucleus in each of these, positive, right? And those electrons that are being shared between the 2 atoms, because they're negatively charged, they're going to be attracted to the nucleus to the guy on the left, but they're also going to be attracted to the nucleus to the guy on the right. And that's what sort of locks them into place and keeps them there. And so they're just going to flow away. There's that mutual attraction to the nucleus of both bonds there. This is what is known as a covalent bond, the sharing of electrons. And this is the type of bonding that occurs in nonmetals when they get together, because, again, neither one wants to give away their electrons. So sharing is the best that's going to happen when you get 2 nonmetals basically together. Any questions on that there? So again, as I mentioned, that is a covalent bond, and that attractive force between those negatively charged electrons and the nucleus is what holds them together. We look at another example like fluorine. Each of the fluorines here, which obviously is the same element, will have 7 valence electrons. And again, they're definitely going to share those electrons. And that will give you, as you can see on the bottom there, something that looks like this. where those electrons in the middle will be shared. So those electrons will count for the fluorine on the right, which gives it 8. Those electrons will also count for the fluorine on the left, which gives it 8. Once again, 8 being noble gases. So as you can see here in covalent bonding, the way we're able to get everybody to the noble gases is actually through sharing the electrons. In ionic bonding, the way we get everybody to noble gases is transferring the electrons. So there's a different type of bond that's happening between ionic and covalent in that case. Now, again, you could also draw this line where they're sharing instead of dots, which is perfectly good as well. Now, when we look at this, there are a couple of different types of electrons. And all these dots here, which are not involved in bonding, and by the way, I know that because frankly, there's no other element on the other side of the dots. So there's nothing there. They are what are referred to as non-bonding electrons, or if you're old like me, lone pairs. I would probably call it lone pairs most of the time. Lone pairs and non-bonding electrons are the same thing. They're basically electrons that are not involved in a bond. Now, these electrons right here, which are involved in a bond, also has a special name, very creative. They are known as bonding electrons. So bonding electrons are the ones involved in bonds. Non-bonding electrons are the ones not involved in bonds. When you draw Lewis structures, you should always show all those electrons, the non-bonding electrons and the bonding electrons. Any questions on that there? All right, we're laid up there.